All right, welcome to another IAEI News Live program. Today's discussion is going to be on circuit breakers. Title of this session is Circuit Breaker Basics, and it starts now. Right. Well, welcome to another session. And it is Tuesday. And, today, this is a recorded session. It is my time, 7 a.m. Tuesday morning on the 19th. And today is Code Making Panel 2's second draft. I keep saying first draft, second draft meeting. So I will be, at the time this is airing, I'm going to be on Code Making Panel 2, listening to debate and looking at the suggested changes for Articles 210 and 220. So I wanted to make sure I did not miss a Tuesday for IAEI news, and here we go. So today's discussion is going to be on circuit breakers. If you recall, I did a session, I believe it was last week. Link will be up above, either up here and down below. I did a session on panel boards, and that was probably going to be one of many on that topic to come. This is going to be the foundation for circuit breakers, like that was a foundation for panel boards. So today we're going to talk about circuit breaker basics. I want to cover some of the basic information about circuit breakers for all of you, and let's get it started right now. So circuit breaker basics. The first place we're going to go, and I should have had this ready already, is there we go. I'm back. Article 100 in the National Electrical Code, and the version I'm using right now is the 2020 version of the NEC. Now, the definitions, I'll give you some word of advice. The definitions are being looked at and probably are going to change as we move into the 2023 cycle for a couple of reasons. One is there are changes coming into the 2023 code cycle that basically are moving all the definitions into Article 100. As in the process of doing that, obviously definitions are getting some attention, probably more than what they would have in the past. So we made some definition changes for circuit breakers as part of we're making changes. We're in mid process of making changes for circuit breakers in the 2023 code cycle. So take a look at that. Be mindful, this session right now is being done in October of 2021. And we are in mid-cycle. We are just starting the second draft meetings. In fact, I sit on panels 2 and 10. I do not speak on behalf of NFPA. I do not speak on the behalf of IAEI. I don't speak on behalf of code making panel members on the panels that I represent, that I sit on. Everything you hear coming out of my mouth is going to be my opinion. So question it and do your homework. So these panel 10 governs the definition of circuit breaker. And if you look on page 70-33 of the 2020 code, you will see a quite lengthy definition, because it's a definition with sub-definitions. And the NEC defines a circuit breaker as a device designed to open and close a circuit by non-automatic means and to open the circuit automatically on a predetermined overcurrent without damage to itself when properly applied within its rating. Now, there's a lot in that one little sentence. We understand that it opens and closes in an automatic or a non-automatic fashion. So I can turn a circuit breaker on and off. That tells me that there's a switching mechanism built into a circuit breaker. It also tells me that it should open automatically on an overcurrent. Now, the next question you have to ask yourself is, what is an overcurrent? Let's take a look at the definition, because there is a definition of an overcurrent, and it's also governed by Codemaking Panel 10. Overcurrent is any current in excess of the rated current of equipment or the ampacity of a conductor. It may result from overload, short circuit, or ground fault. Any of those three conditions. So a circuit breaker has to be able to respond to an overcurrent, which could be a short circuit, an overload, or a ground fault. And we're going to understand how it does that. And we're going to understand how we determine how long it will take for a circuit breaker to open based upon an overcurrent. Now, there are 5 little subdivisions. I don't know what you call these. We can't call them first level subdivisions. They're like definitions in a definition, which is kind of odd, but I believe we're addressing that. Time will tell. You got to check out the 2023 code cycle. So let's take a look at what does the definition of, inside the definition of a circuit breaker, we have adjustable as applied to the circuit breakers. So you can have an adjustable circuit breaker. And what that's telling us is that a circuit breaker can be set to trip at various values of current. Not all circuit breakers, but a circuit breaker can be set. How do we do that? How do we get that done? I didn't bring a circuit breaker with me. Anyway, there are dials, and we're going to see pictures of it. There are dials on the front, or there are dials on the front of some circuit breakers, or there could be an electronic interface that I use, or you use, to adjust the settings. So that's the first little, diversion. The second is, it says instantaneous trip, a qualifying term indicating that no delay. So it's opening without an intentional delay. So instantaneously, the circuit breaker doesn't think about it. It has to automatically trip and open based upon an overcurrent. So no intentional delay. That is what we're calling an instantaneous trip. Now, the third little subdivision, it says inverse time. All right, so inverse time. Oh, I need these. A qualifying term indicating that a circuit breaker does not have any adjustment to alter the value of the current at which it will trip or the time required for its operation. So, I'm sorry, inverse time. I read the wrong one. A qualifying term indicating that there's purposely introduced a delay in the tripping action of a circuit breaker, which delay decreases as the magnitude of current increases. Inverse time is the higher the current, the faster the clearing time. So this is an important, in my opinion, this is a very important piece to understand when it comes to circuit breakers and fuses, which we're going to have another session on fuses. Inverse time, and you're going to hear what we call an inverse time current characteristic curve. The higher the currents, the faster the clearing times. Why would that be important to understand? If I want to understand arc flash, and I've heard people say, lower currents give me lower incident energy. That's not necessarily true. Why? Because I have to understand the concept of an inverse time as the qualifying term for a circuit breaker. Inverse time means lower currents can produce longer clearing times. Lower currents, longer clearing times. Longer clearing times on arcing currents produce higher incident energy. This is why we're talking about the fundamentals of circuit breakers here, because this is a very fundamental principle that's important to understand, especially when we're trying to understand more complicated concepts such as incident energy. I always tell people, as an engineer, we learn fundamentals. We learn how to derive equations. They teach us not here's the equation. They teach us how to get to that equation. What physics and how do we arrive at what we know is to be true? And once you understand these fundamentals, you start to understand a little bit more of the fabric of what we're talking about. Inverse time is a critical piece that we should all understand when it comes to an overcurrent protected device, because that applies to us: a molded case circuit breaker, insulated case, power circuit breakers, and fuses. And then we also have non-adjustable, which means you don't have an adjustment. A good example of a non-adjustable circuit breaker is your standard residential 20, 15 amp circuit breakers. You want a 20 amp breaker, you got to buy a 20 amp breaker. If you bought a 20 amp breaker and you wanted a 15 amp breaker, you're going to go back to the store and buy a 15 amp breaker. You're not adjusting any dials on a residential circuit breaker yet. Now, settings: the value of current, time, or both at which an adjustable breaker is tripped to set. So I can change the settings of a circuit breaker, and we're going to understand those settings here shortly. All right, so those are the definitions within the National Electrical Code, Article 100. Remember, we hit circuit breaker and we hit overcurrent. We could touch on overload. Let's take a look at overcurrent again, because within the definition of overcurrent, we have other terms that we use within the code book. Remember, overcurrent can be a short circuit, an overload, a short circuit, or ground fault. What is an overload? An overload is operation of equipment in excess of normal full load rating or of a conductor in excess of its ampacity, that when it persists for a sufficient length of time would cause damage or dangerous overheating. A fault such as a short circuit or ground fault is not an overload. So a overload is when I am overloading the circuit. Let's talk about a conductor's ampacity. If my conductor's ampacity is 20 amps and I'm at 25 amps, I am in an overload situation. My current is not significantly greater than the rating of that circuit. It's overloading it such that if it persists for a sufficient period of time, sufficient length of time, I could create damage. And we're going to understand the portion of the time current characteristic curve of a circuit breaker that gives you your overload protection. And we're going to understand what we're doing inside of that circuit breaker that makes that possible. All right, so that's an overload. How about a short circuit? Now, in the 2020 code, if I am not mistaken, which I could be mistaken, we defined fault current. And it was the first introduction of this term in the NEC, but it was just introduced at this time, just prior to the NEC's development process. It was introduced into NFPA 70E, Edward, for safe work practices, because fault current is another important term that we, now I have my own opinions on this change, but I'm not going to tell you about my opinions unless you specifically ask me for my opinion. But I'm going to tell you what the code says about fault current. Now, fault current, and they give us a nice little diagram. It's beautiful. An informational note for available fault current. So fault current available, or available fault current, and then fault current. So fault current is the current delivered at a point on the system during a short circuit condition. So we know that a fault current isn't an overload, it is a short circuit condition. Now, an available fault current is the largest amount of current capable of being delivered at a point on the system during a short circuit condition. So it's the largest amount of current that can be delivered at a point under a short circuit condition. Now remember, from a circuit breaker's perspective, what did we say? A circuit breaker has to operate on an overcurrent. An overcurrent includes a short circuit, so it has to be able to stop the flow of your available fault current at a point in the power distribution system that it's going to be called upon to open. So the definitions help us, and I know definitions can be very boring. They can be challenging to stay awake in discussion, but it's really important to understand. There's a lot in the definitions for a circuit breaker: overload, short circuits, ground fault. Let's talk about ground fault. Did we talk about ground fault current? There's let's take a look. Ground fault. A ground fault is an unintentional electrically conductive connection between an ungrounded conductor of an electrical circuit and the normally non-current carrying conductors, metallic enclosures, metallic raceways, metallic equipment, or earth. Now there's another one. That is your ground fault. So a circuit breaker has to be able to respond to an overcurrent, which includes a short circuit, which we know is available fault current, an overload, and ground fault current, which is this connection to the metal components and all this other good stuff. So that's what we respond to. That's what, and it does it in an inverse time current characteristic. So the higher the more current you feed the beast, the faster it responds, which could be good for an arc flash reduction. Just saying. All right, I think I feel comfortable with definitions. Do you? Hopefully you do. Now here's the three different types of circuit breakers. We got the molded case. We got the insulated case. We have the low voltage power circuit breakers. I want you to understand why we've got these three pieces, these three types of circuit breakers, where they might be used, where you'll find them, why it's important for you to understand the differences between these three types of circuit breakers as a fundamental. Remember, this is your foundation, which is freaking scary. All right, molded case circuit breakers. What are they listed to? Well, Tom, I'm glad you asked. Molded case circuit breaker, excuse me while I get something here. A molded case circuit breaker is listed to UL 489. Now, UL 489 is the standard for molded case circuit breakers. Now, there's you typically will not download UL 489. You'll use which brings up a good case. I will probably remember I had a special event for IAEI News Live, if you recall. Last week, I had a special guest where we talked about, we had Eric on, and we talked about this new NFPA link and the great resource in NFPA link. I'll try to put the link to NFPA link either up above. I know it's going to be down below. But what we should do is I need to get somebody from UL on here, and we need to talk about product spec, or whatever they're calling it today. Remember back in the day, I used to hate when people older than me used to say that. I used to get really irritated back in the day. Now I'm saying back in the day. So back in the day, we had the white book. And you could probably, if you Google UL white book, they're still out there, some PDF versions of them puppies. And in my opinion, I think it's a very good resource. But there is now UL, I believe it's product spec. But what I'm going to do is I'm either going to get Mr. Jeff Facteau, which you know him. Maybe Tom Lichtenstein. I might get Mr. Thomas Lichtenstein. I don't know. I'll get somebody from UL on our program here to help us understand product spec. But let's talk about molded case circuit breakers. Molded case circuit breakers listed to UL 489. You'll find these, and I added 10 amps. I used to say 20 amps or 15 amps up to 2,500 amps. But just recently, we're seeing copper-clad aluminum being recognized in the National Electrical Code down to 10 amps. So, and we do make 10 amp circuit breakers. So panel 10 just recently in the 2023 code cycle, which we still aren't done with, but I believe you're going to see recognition in the National Electrical Code for a 10 amps molded case circuit breaker, which is a good thing. Voltage ratings from 120, 240, 480 up to 600 volts. You're not going to find a medium voltage UL 489 molded case circuit breaker. Just saying. Frames. Now you'll hear, remember I have a 10 amp trim to a 2500 amp frame breaker. Frames are complicated. I'm going to get into frames once I start getting into the trip curves, so I'm not going to touch on that right now. But that's the ampere range. So I have frame ratings up here that is your 15 to 2500 amp ratings. Frames are a little different than the ampere ratings. So, oh, it doesn't say frame. I saw it's from. So that's not a frame. That's a continuous ampere rating. So that is actually, I was just going to go and correct it, but no, it is. It's right. It's a continuous ampere rating from 10 amps to 2500 amps. We're going to talk about frames here when we start getting into a little bit more complex, and we start talking about trip curves. What else? Oh, a molded case circuit breaker. You know how you can tell a molded case circuit breaker from any other circuit breaker out there? It has a handle on the front that goes up and down or left and right. You're going to physically push something up and down to turn it on and off. And why is that important to understand? It is important to understand that little detail, and I'm looking for a book. Oh my. NFPA 70E table method. I know all of you are familiar with the NFPA 70E table method, and I know where it's at. It's in my bag. And the reason it's in my bag is because, no, it's not. I took it out. Here it is. You should always have your 70E document readily available wherever you're at. In fact, multiple copies spread throughout the house are I think critically important to make sure that you have ready access, because readily availability. We're going to be in Article 130 within this wonderful resource for life-saving concepts and ideas and requirements. Table 130.7 Charlie 15A. What is that table within the within the NFPA 70E safe work practices? This is our PPE category. We call it the table method. Now, if you look at table 130.7 Charlie 15A, it's going to give you different pieces of equipment like panel boards. It's going to give you 600 volt class motor control centers, all this good jazz. But if for each of these scenarios in this table, if you look at it, you'll see where it says parameters, maximum of 25,000 amps of available fault current. I'm just reading off of the first row, which is a panel board, 240 volts and below. Maximum of 25 kA available fault current. Maximum of 2 cycle fault clearing time. That's an important piece. And if you look at the informational notes to this table, it'll tell you that molded case circuit breakers will typically have a 1.5 cycle clearing time. And that's going to be in the instantaneous region. Now, if I look down through everywhere where it says 2 cycles, so it says 2 cycles for the first row, panel boards, being fed from a 2-cycle device, molded case circuit breaker. And that's for 240 volts and below. Then there's a 240 to 600 volts. And then the third one says 600 volt motor control center, fed from a 2-cycle device. You skip down to other 600 volt equipment, and there's the 2 cycles. Those are the only 4 locations in this table that reference a piece of equipment being fed from a 2-cycle clearing time device, which is a molded case circuit breaker. And look at the arc flash PPE categories for those 4 areas. The first one for 240 volts and below is a PPE category 1, which tells me I'm in a 4-cal outfit. The other 3 are PPE category 2, which tells me I'm in an 8-calorie outfit. Everything else, which would include a 20-cycle clearing time, a 30-cycle clearing time, a 15-cycle clearing time, are not molded case circuit breakers. They are something else, and you got to look down at the table, and we're going to talk about those, insulated case and power circuit breakers later. So for the apprentices out there, for all of our journeymen out there, they need to be able to identify a molded case circuit breaker because that helps them apply the table method within 70E. If I can identify that that's a molded case circuit breaker, I know I'm in a 2-cycle clearing time for my fault currents, especially for high fault currents. And that helps me determine my personal protective equipment. All right. So you're going to find interrupting capabilities, I'll say not 22K, down to 10K for residential circuit breakers, a 10K device, from 10K to up to 100,000 amps. Anyway, and where am I going to find a molded case circuit breaker? Molded case circuit breakers are probably the most common overcurrent protective device you will find in a power distribution system. You're going to see them in panel boards. You'll see them in switchboards, in motor control centers, panels, industrial control panels, residential. You'll find them in a lot of applications. Now, the other 2, insulated case. An insulated case circuit breaker is a UL489 device. A lot of people don't understand that. Technically, an insulated case circuit breaker, technically, is a molded case circuit breaker. Why do we call it an insulated case circuit breaker? That's a good question. It's a marketing thing. It's a marketing term. It has nothing to do with it. And when I say a marketing thing, I don't mean that in a bad way. I mean that we're trying to help people understand that the insulated case circuit breaker is a different beast meant for a different perspective. For example, you'll look that I can buy an insulated case circuit breaker down to 800 amps, and that's a frame. That's not a trip. So an 800 amp frame circuit breaker, I could adjust that down to, 200 amps if I wanted to. Whatever that trip unit will let me adjust it down to from a current rating perspective. So I can take an 800 amp breaker and make it a 200 amp breaker. Why would I do that? An insulated case circuit breaker is bigger. It's got more beef. And the reason is in the time current characteristic curve. And I'm going to show you trip curves for a specific insulated case power circuit breaker and a molded case circuit breaker a little bit later in our discussion that will help you understand the differences between these 3 devices. Suffice it to say, I'm going to see insulated case circuit breakers closer to my service entrance equipment and sometimes in my service entrance equipment. And the reason I buy an insulated case circuit breaker is because I want to keep those contacts closed longer for higher fault currents. Why would I want to do that? I want my little puppies downstream to open and clear faults so that I maintain reliable power distribution system to everybody else. So you isolate your portion of the system while I hold my contacts closed and let you do your job. That's a good manager, right? It's a good leader. Think about leadership. Leadership is not micromanagement. It's not about telling everybody what to do. It's not about shutting the plant down the moment one little issue happens in a plant and making everybody run and scurry. It is about letting the overcurrent devices closer to the action do what they do best. Think on their own. Respond to those overloads. Respond to those short circuit currents. Respond to those ground fault currents. And isolate the problem without disrupting the entire facility. The insulated case circuit breaker gives me the ability to hold those contacts closed. And now, if you think about what does it take, imagine the amount of magnetic forces that are exerted on a power distribution system with one cycle of current. And if I can pull this up, I'm going to pull this up. Cable whip. What I will typically do is help people understand the magnetic forces associated with a short circuit in a power distribution system. And we use what we call the cable whip video. And I'm just flying off the cuff here. So I'm just going to do WHIP and see if I can find it really quick. It's actually in a presentation, so I'm going to open up a different presentation and do this. So, but in any case, when I'll just talk while I'm looking, the insulated case circuit breaker and the power circuit breaker, for all that matters, the fundamental principle is I want to keep my contacts closed during these higher fault currents. So what that does is helps me make sure that all of the power distribution system components work downstream and do their job. So I'm holding my contacts closed, and think about a circuit breaker has a set of contacts where the magnetic forces wants to blow those contacts apart. I am holding those contacts together underneath those magnetic forces of due to the fault currents. Now I have the video. This is a 1 cycle clearing time, and I'm just going to I'm going to hide me. I don't know how to do that, but I'm going to figure it out. And I'm going to show you now what you're going to see. You have 26,000 amps flowing through a 2-watt conductor, 90 foot of 2-watt conductor. 1 cycle clearing time. These are the magnetic forces exerted on the power distribution system. Well, I guess that's not going to happen. Anyway. Yep. Nope. That's not going to happen. All right. So I got to find the actual video. And that's just an image. Why would I have just an image in my presentation? Anyway, so let's I have it in a different presentation. While I'm looking, now where will I find an insulated case circuit? Insulated case circuit breaker is 800 to 6,000 amps, up to 150,000 amps of interrupting rating, which I think is another important piece of the puzzle here. Think about from an interrupting capability. Now I can get to higher. What you'll typically see with insulated case circuit breakers is the what do you call it? The interrupting capabilities. I can get higher interrupting capabilities, and typically what I'll employ are limiters, basic like fuses to help interrupt and stop the flow of current. You'll find these in switchboards and switchgear. You are not going to find an insulated case circuit breaker in a panel board. All right. So you're not going to find an insulated case circuit breaker in a panel board. Now, I did find my screen, which I'm going to be able to show you. Now, again, I'm just going to point out that this video is of a approximately 26,000 amps, non-current limiting. So this is going to be one cycle of current. One cycle of current, 26,000 amps through a conductor. All right, I'm going to show that to you one more time. So that is a significant amount of magnetic forces that a insulated case circuit breaker or power breaker has to hold those contacts closed and not achieve an unintended rapid disassembly in the field. Now, a low voltage power circuit breaker now is listed to a ANSI IEEE standards, C37.1316 and C37.17. Typically, again, 800 to 6,000 amp frame and an interrupting capabilities of 42 to 100,000 amps or current limiting up to 200,000 amps. You're going to find these in switchgear. You're not going to find them in switchboards. These are going to be switchgear type of components. The reason we say, the reason I'll say switchboards, I'm going to take that out. Found in an enclosure, it's going to be in a switchgear type of application. And your low voltage power circuit breakers, again, they're going to be fixed or draw out capability. Remember, the enclosures are going to be very large. And the UL 1006 is the standard. ANSI C37 is also the standard. So if I was going to give you a UL reference, it would be 1006. Up to 635 volts AC, the same thing for an insulated case circuit breaker, and the exact same range of currents, typical ranges that you'll find for those circuit breakers. All insulated case, because it's a UL 489 device, all insulated case circuit breakers and molded case circuit breakers are going to have an instantaneous. The low voltage power circuit breaker is the only circuit breaker that will not have, or could not, may not have an instantaneous trip on its trip curve, which we're going to talk about here in a few minutes. So someone would ask, now the low voltage power circuit breaker is it's a beast. They're large. The mechanisms are huge. They're very large. Why? Because I can hold my contacts closed for up to 30 cycles. 30 cycles. What is one cycle? In a 60 hertz system, one cycle is 1/60. It's 1/60th of a second. It's 0.0167 seconds. 30 of those puppies is 0.5 seconds, 1/2 of a second. That video you watched was one cycle, 0.0167 seconds, 1/60th of a second. A power circuit breaker is going to hold those contacts closed for up to 1/2 of a second. Think about the magnetic forces and the stresses on those contacts in that equipment. And how do I keep them closed? How do I make sure I have enough force? It's the springs, it's the beef I bring to the table. A low voltage power circuit breaker is a big boy. Insulated case circuit breakers are smaller. They're not going to be able to hold those contacts closed for up to a half of a second as high as this beast can. It's going to go into its instantaneous region without an intentional delay at lower current values because it just can't hold those contacts closed. Remember, the hardest part for a circuit breaker is to keep the contacts closed. And what you want to not have is chatter on those contacts. That is what we call ungood. Because what does chatter do? Chatter creates dimples. Dimples are cute on a person, but they are not cute on a circuit breaker, whether it be molded case, insulated case, or power circuit breaker. All right. Now, supplementary overcurrent device. There's another type of device that you might find in a power distribution system. And a supplementary device, if you look in 240.10, Article 240.10 in the 2020 code. I just want to make sure it's the same title. Nothing's moved. Nothing's happened. Nothing to see here. Still says the same language. These devices aren't the same as a molded case circuit breaker, insulated case circuit breaker, or power circuit breaker. They are supplementary. They're not listed. They're listed to UL 1077. It's not a 489 device. They are not suitable for branch circuit protection. They do look like a regular circuit breaker. And if it was a fuse, they look like a regular fuse, but they are not listed that way. So you've got to make sure, and this is why we look at listings. This is why we require listings. This is why it's important that we understand the proper application of products in the field. Now let's take a look at the physical construction of a molded case circuit breaker. You have these are the terminals. You have a line and load. This is the terminal connector, I believe, on the load side of this circuit breaker. The other ones are on the line side of the circuit breaker. So your source would be at one end or to other. And if it was a PV application, you know, this could be the source. So that may not be may not be the load current. That could be the actual source. If it was not labeled as line and load, you could backfeed through this circuit breaker, and it could be a PV connection. You never know. Systems are getting more complicated these days. You have a trip bar. You got to look inside this breaker. It is kind of complex, right? There's a lot of moving parts. There's a lot of things going on. There's your contact way over there, and it rides inside of these arc extinguishers, which we're going to learn what those are here in a second. Your contact is a very important piece of the puzzle, because remember, under fault conditions, this is a molded case circuit breaker. What did we say about insulated case and power circuit breakers? They can hold those contacts closed longer. So I need more beef. I need that arm is going to be beefed up. There's going to be bigger, beefier springs in there. And then you have the molded case holds it all together. You got a handle. There's a great indicator that this is a molded case circuit breaker. A molded case circuit breaker is going to have a handle on the front like that. Insulated case and power circuit breakers, push buttons, and a charging arm. Contacts. This is what breaks the flow of current, a physical contact. This is good stuff, right? So you have that standard linear design, which looks like this, and they just open and close. But what the circuit breaker manufacturers have recognized is we should leverage physics. Imagine that. Imagine that. Right-hand rule, or I don't know, some people call it a left-hand rule. I was always trained power systems engineer, right-hand rule. Anyway. The magnetic forces, you've taken two magnets and put them, try to touch them. If you've got the same polarities, they want to push each other apart. Opposites attract. The magnetic fields, we can leverage that to make a faster clearing time. And what am I doing? I'm leveraging the magnetic forces that we just saw in that video to blow these contacts apart. Like I said, the hardest part, holding them closed without chatter. The arc extinguisher's job and function in life is to divide and conquer that arc as it's drawing up in between the plates. the arc will dissipate and be cooled by those plates. The distance that we separate the plates, the gaps that we provide, help extinguish the arc. It's an art unto itself on creating a good arc extinguisher. But you can see what it does, and it will expend the gases. And then on the other side of the arc extinguisher, you have arc chutes, which help vent the gases that are expelled due to the interruption, the stopping of the flow of current in that device. Every circuit breaker is going to have an arc chute that expels those gases. And then the arc extinguisher helps extinguish and cool that arc and stop the flow of current. It's magnificent. All right, so here you got your thermal protection. Your thermal protection. It's typically going to be a bimetal, unless it's electronic. How the thermal works, and I have a video that demonstrates this. You'll see that the bimetal will heat and bend and drop the lever, and the instantaneous will be, I call it the clapper, where it will pull in a piece of a plate, drop the latch, and open the device. And there's your and we show it as a coil, and honestly, it's not quite that way. And I have the video that I have helps demonstrate that, which I think is my next slide. So let's take a look at and what I'm going to do is my hide transition is going to be a fade. So all right, let's take a look at this video together. All right, so what you're looking at, you got an internal view of a typical residential multi-case circuit breaker. There's your magnetic trip. That is that's your magnetic, I call it the clapper. The magnetic forces pull in this plate, which holds the latch that holds that breaker closed. And this is in slow motion, when that magnetic forces pull that plate in, the latch will drop and the circuit breaker will open. Now the contacts just, I'm going to pause this real quick because I want to draw something here to help you understand what's going on. So this is the bimetal. This is the magnetic clapper, I call it, whatever, that pulls in. This copper conductor is a flexible conductor that basically connects the bimetal and the instantaneous portion with the contact arm. And this is the contact arm here. That contact arm, and I'm just going to back this up. Erase all of this, erase all the ink on slide. Let's back this up a little bit. Whoop. Okay, now I want you to watch this again. There's that magnetic trip. Okay, now what I'll point out here is that this magnetic arm, you'll look at its position. Remember, this side here goes on the bus inside of the panel board. Over on this side here is where we land our conductors going to the load. So the current is flowing from the source through this contact arm. Because of this braid, it flows this way, up and back down and out. And this is the bimetal that will bend, and this, which is being indicated here, is what we call the instantaneous portion of that internal linkage. All right, so that's basically what's going on. Now let's continue watching the video. Now what we just saw was the instantaneous. So this is a very high fault current, and every molded case circuit breaker and insulated case circuit breaker is going to be equipped with an instantaneous. And you'll see once the magnetic forces get so high, it will suck this plate in, which will drop the latch and open those contacts. And that effectively opened that circuit breaker. Now, the next portion of this video is going to look at the thermal side. This is the continuous heating. This is the overload region of a circuit breaker that takes seconds, maybe minutes, to actually open the device on an overload. Now that whole bimetal is going to bend and the latch is going to drop. Now watch how it bends. Now there's force, there's friction there too. And then it drops. So that entire assembly was bending. That's what a bimetal does. And now we're going to just see the whole thing at full speed. Now there's the latching. That's why you turn it off first and then back on. The instantaneous drops the latch, opens it as that sucks in. Now you turn it off, you latch it, and you turn it back on again, and you close the contact. And now I'm going to bend that bimetal, and that is going to open, drop that latch, and open the circuit breaker. And that, my friends, is how a molded case circuit breaker interrupts the flow of current. And what you just saw created this time current characteristic curve. So the bimetal, the bending of that bimetal is what generates this portion of the curve. That's and you see how fat that band is? If I can get this right. You see how fat this band is right here? That tells me that for any given current, say this is a 20 amp circuit breaker. If I had 100 amps, if I plotted 100 amps, and it would probably be, I don't know, about right in here somewhere, 100 amps would take either wherever it crosses the bottom and over, or wherever it crosses the top and over, that much time. And that difference of time is basically what we saw in that video. You saw how the friction of that latch has to open. And you saw how that plate has to close, has to be sucked in by those high magnetic currents. Those plates are what gives you this curve down here. And look how much time you have, anywhere from 0 seconds up to 0.02 cycles or 1.5 cycles, right? We saw that in 70E. 70E says that a molded case circuit breaker is a typical clearing time in that instantaneous region is 1.5 cycles of current, of time. So that's how we create these. Now, when you think about a time current characteristic curve, you got to understand what we're talking about here. Across the bottom is current, and up the side is time. And you'll see it's a log to log, logarithmic, logarithmic to logarithmic, a log to log type of paper. So the distances between each of these portions, like for example, I have, this is 10 amps. This is 100 amps. If I split this difference directly in the middle, that would not be 50 amps. Okay, this is 10, this is 20, this is 30, this is 40, this is actually 50. It's a little bit further off to the right because it is a log to log paper. And current or time is the same way. I got 0.01 seconds here. I've got 0.1 seconds here. This is 0.02. This is 0.03, 0.04, 0.05, 6, 7, 8, 9, and 10. And you'll notice they get closer and closer and closer together. That is basically what logarithmic paper does for me. And what that means is that instead of this paper going from 10 to 100,000 amps and being 3 miles long, I can shrink it down to a much shorter time scale or scale. And we plot the performance of a circuit breaker on a time current characteristic curve. So inverse time, higher fault current. So at 10,000 amps, this breaker is going to trip in faster, and this is 0.01 and this is 0.02. So I'm at 0.018, somewhere in that ballpark. At 1,000 amps, which is right here, this breaker is going to trip anywhere from 0.01 seconds or 0 all the ways up to 1, 2, 3, 4, about 5 seconds. So that breaker could take anywhere up to from 0 to 5 seconds to open if for 1,000 amps. For 200 amps, let's just clear this out, erase all. So this is 200 amps. 200. This circuit breaker, I follow this all the way up, and I'm not good at drawing straight lines with a mouse. It can trip anywhere from here. Boy, that is terrible. I'm going to use my eraser on that one. Anywhere from here, which is right here, to about right here, which is about right there, right? So what do we know? If this is 100, this is 90, this is 80. Anywhere from 80 seconds to, this is 100, this is 200, this is 300. So we're going to call this about 290 seconds. So for a 200 amp current passing through this circuit breaker, it's going to trip anywhere from 80 seconds to 290 seconds. And that's just ballpark figures based upon trying to read a time current characteristic curve here. So that's basically how you would interpret what these trip curves tell you. And remember, you look at the current that's passing through this device. I don't care if it's a ground fault. I don't care if it's a short circuit. I don't care if it's an overload. I don't care what it is. It is current of 200 amps passing through this device for whatever reason. It's going to take anywhere from 80 to 290 seconds for that device to open. That is what we call the overload region. Over here is the instantaneous region. And these are just, examples, continuous examples of, for 1500 amps, the maximum clearing time is 2.8 seconds. For 500 amps, the maximum clearing time is 20 seconds. For 300 amps, the maximum clearing time is 65 seconds. For 80 amps on this breaker, it will never trip. This is a 100 amp circuit breaker. This is a 400 amp circuit breaker. It demonstrates that I can adjust the instantaneous. I can move the instantaneous down and have it trip faster on lower fault currents. This is an electronic trip unit. We put a brain on the overcurrent device. Why would we put a brain on an overcurrent device? Because we can. Why would I do that? Look how tighter the trip curve bands are. Remember these. Look at these. Look how fat that band is. Why is that band so fat? It's because you saw the mechanical nature of that overcurrent device. Look how nice and postured these are. Very nice and skinny bands, and they're even smaller for various overcurrent protected devices. And what another thing that an electronic trip unit does for a circuit breaker, remember, this is putting a brain on a device. So now I'm not relying on this latch. I'm not relying on this bimetal bending and all the frictional forces. Now on an electronic trip unit, I can control with some level of better precision on when this device opens based upon the amount of current flowing. And I can make this curve change as I see fit. And typically it's going to, the configuration of this curve, why would I want this? In some cases, I can make that curve look like this, straight over and up, and provide a nice knee. Why would I do that? I might want to provide better protection in this region for, say, a motor, a transformer, whatever. I might want to shape this curve because of selective coordination, because I want to stay out of the way. Let's say that I have a fuse curve that comes down like this. And I have a lack of selective coordination. What might I be able to do? I can do that, or I can turn it off and say, now I've got clear separation in between these curves in this region. I no longer have a problem. All I did was change a set point on this device to establish a better clearing space to make sure that the fuse downstream goes before the circuit breaker upstream in this region of the time current characteristic curve. So the electronic brain, when we implanted the brain, the electronic trip unit inside of a circuit breaker, it helped us solve some application problems and challenges that the power systems engineer would have in coordinating or providing better levels of protection. And remember, this is a fundamental. So moving forward in this category of discussion, we're going to have experts and we're going to beat this breaker up. We're going to understand all of the details associated with why this brain is there, how it works, how it operates, how it functions. So you got to subscribe to this channel and make sure you don't miss one of these discussions. There is an example of an electronic trip unit. And you can tell it's an electronic trip unit because look at these nice, sharp, squared off lines. You don't get that from a thermomagnetic circuit breaker. You don't get this type of detailed straight lines and angles on a molded case circuit breaker that does not have an electronic trip unit. This breaker has much more functionality than the other standard thermomag breaker does. I can move this curve left and right. I can change this from a 600 amp breaker to a 400 amp breaker possibly. I can take it down to a 200 amp breaker if I wanted to, from adjusting a trip setting on the faceplate of this device or via an electronic interface. Now, what I'm showing you here, I'm showing you 600 amp circuit breakers. Let's just take a look at this. This is a 600 amp molded case circuit breaker. Look, it's a 600 amps molded case circuit breaker. This is current times 100. So I know this is 1,000. This is 10,000. The instantaneous pickup, 2,000, 3,000, 4,000, around 5,000 amps, we'll call it. I'm still in the short time delay. 5,000, 6,000, about 7,000 amps. I'm into the instantaneous pickup of this 600 amp breaker. Around 7,000 amps. This is a 600 amp insulated case circuit breaker. I'm well above 6,000 amps, 7,000 amps. And look, I have a delay. How did I get this delay at 10, 20,000 amps? I'm holding those contacts closed. I brought more beef. This 600 amp breaker is much bigger than the previous molded case circuit breaker, but it's still 600 amps. But what am I getting out of it? I'm holding those contacts closed for those higher fault currents. And this is a low voltage power breaker. Look, all the ways up to its instantaneous, all the ways up to its interrupting capability. This is all times 100. So I can get 30 cycles of delay up to the interrupting rating of this 600 amp breaker. This is what bringing beef to the table does for you. Why might I want this? Service entrance equipment. I want to ride through all the short circuit currents that are going on downstream. Why? Not because I just want to, wreak havoc. No, I want the downstream devices to isolate the faults locally and not take out the main. I want that intentional delay. I might want all those motors to start and not take out the main. I might want all of those transformers to energize and not take out the main. There are a lot of different reasons why you'll see a power circuit breaker over an insulated case circuit breaker. And I'm telling you, it all comes down to the resume, which is the time current characteristic curve. Interrupting ratings is how much current I can stop from flowing in a circuit breaker. Circuit breakers do not have a short circuit current rating. They have an interrupting rating. It's defined in Article 100. There's another term, Article 100, interrupting rating, the highest current at rated voltage that a device is identified to interrupt under standard test conditions. Code Panel 10. 110.9 tells us that the rating has to be greater than the available fault current. OSHA tells us how important this is. Because why? Because you can, if you don't do this correctly, you can achieve an unintended rapid disassembly in the field. If you exceed the interrupting rating of a circuit breaker or a fuse,
this is a serious misapplication.
It is a serious misapplication, like he said. I don't care if it's a fuse or a circuit breaker. Interrupting ratings are very important, and it's at rated voltage. The highest current at rated...
this is a serious misapplication.
The highest current at rated voltage. So voltage and the amount of current is going to play a role. Now, 240.60C, 240.83C tells us if it's not labeled, this is what you assume. And supplemental protected devices don't have an interrupting rating. If you look at a circuit breaker, a switch, a fusible switch, whatever, I don't care what it is. If it's a short circuit current rating, if it's a fusible switch or some assembly, voltage is very important when we're talking about how much current we can stop the flow of current. How much voltage at whatever voltage. So for this circuit breaker, at 240 volts, I can stop 65,000 amps from flowing. That's a pretty big number. But if I'm actually applying this on a 600 volt system, it's only 18,000 amps. Remember, voltage is pressure. So when you're looking at interrupting ratings, don't make the mistake of stopping at that first column. I've seen it before. I've had inspectors. I had an electrical contractor call me and tell me that I needed to talk to the inspector because he didn't know what he was talking about. And he told me he had a one of my circuit breakers, and he sent me a picture of my literature, and he said, look, your breaker can interrupt 65,000 amps. So I called the inspector. I'm like, this guy's got a point. I called the inspector and I said, hey, Mr. So-and-so, I said, I got this guy here. He's telling me that, it appears to me he's using a breaker that's rated for 65,000 amps. And he goes, Tom, he's using it at 480 volts. I'm like, oh, well, then he doesn't have a 65,000 amp interrupting rating. He says, I've been trying to tell this guy that. And then when I called the contractor back and I explained it to him, he's like, oh, fundamental mistake. He just missed it. Bad day, but that's okay. We all have those days. Fuses, same way. They have an interrupting rating. They rely on the amount of voltage as well. And this again, 240 volts, and then if it, see that says 250 volt DC? If your circuit breaker does not have a DC voltage rating and an interrupting rating plastered on the front of that device or somewhere in its piece of information, it is not rated for a DC. Do not apply it on DC. You don't just say, well, it's 600 volts, it's 35, so, or at 480 volts, it's 100. I'm just going to divide that by 2. No, we don't do that. If it doesn't have DC marked on the faceplate, it is not rated for interrupting or for application in a DC application, AC only. Now, series ratings are another aspect from an interrupting capability. It's a fully rated system or it's a series rated system. 110.10 is your short circuit current rating. And remember, when it comes to a panel board, and we talked about this in the previous session, I'll try to put the link up there. Short circuit current rating of a panel board is typically going to be based upon the lowest interrupting rating breaker inside that panel board. So you have to understand interrupting ratings. And if I do a fully rated system, all the overcurrent devices are rated for the amount of current that they are planning to interrupt. A series rated system will have a lower interrupting rating then the available fault current at the equipment downstream of a higher interrupting rated device, which is equipped to handle the available fault current at that equipment. And together, they will stop the flow of current. But I say together, they will get that done because they work together as a team. One protects the other, and that's what we call a series rating. 240.86 is your reference for that, which could be a whole session for another beautiful, wonderful day. And voltage rating. Voltage is these devices are going to have voltage ratings. Don't apply handle ties. If you have a 120 volt rated AFCI breaker or something, any single pole 120 volt rated breaker, and you're going to put a handle tie on it with another 120 volt rated breaker, that is a misapplication. Why? Because the pole to pole, the line to line conductors exceeds the rating of the breaker. Don't do it. 1,000 points of light. Torque. All your circuit breakers are going to have torque published, and this is a thermomagnetic circuit breaker. On the side, it has the torque values. It'll tell you the conductors, 60, 75 degrees C wire use only in listed enclosures, 40 degrees C CTL. And if you want to know the marking, there is a UL marking guide. Yes, there is. And I'll have the link for it down below. Here is the UL marking guide. Okay, molded case circuit breakers. This is July 2016. And again, I'm going to get a UL person on here at one point to help us understand the latest. But we saw CTL on there. So if you want to know what CTL is, let's go to this marking guide. And it says a class CTL circuit breaker for class CTL panel boards or assemblies are marked class CTL or CTL, a class CTL breaker because of its size of conjunction with the physical means, prevents more circuit breaker pulls from being installed than the number for which the assembly is designed and rated. Now, that number used to be 42 circuits, and the 42 circuit rule went bye-bye a few cycles ago. So CTL is not necessarily an important parameter that you need to know. But what's nice about the marking guide is that all of those different markings that are on that circuit breaker are described right here. What 40 degrees C means, special markings, non-conductive enclosure, current limiting, class CTL, delta, 2-pole, 3-phase rated, DC rated 3-pole, 100% continuous, switched duty, independent trip. All of those are described. Any of those markings are described right here in this marking guide. That's going to be down below. And in fact, the markings of line and load, I'll just call that one out too. Line and load identification means that you cannot backfeed through that. Load has to be on the load side. The source has to be on the line side. You can't put a PV source on the load lugs backfeeding through that breaker if it's marked line and load. If it's not marked line and load, you can do that. All right, so we went through a lot on circuit breakers, and this was, again, a primer. This is a fundamentals. This gave you a basic understanding of what you can expect when we start talking about circuit breakers, molded case, insulated case, power circuit breakers. We understand the trip curve now. We understand what inverse means, inverse time. We understand even how it relates to 70E. I'm telling you, this is packed with information. This is why you need to subscribe. This is why you need to click the bell. And this is why you need to subscribe. Okay, so don't forget, subscribe to this YouTube channel. There's sometimes, with times like this, where it's a recorded, and it will be on YouTube. It's not going to be on LinkedIn. It's going to be on Facebook. It'll be right here on YouTube. You need to know when we premiere these videos. All right, this one went a little long. I apologize for that. Thank you for your indulgence in this important topic of circuit breaker basics. We will see you next week, hook or by crook. I'll be on panel 10 meeting, so I'm probably going to be recording the next one as well. But you never know, we might get done quick. Thank you, everybody, for all that you do for the electrical industry and what you do for electrical safety. I want you to stay safe and please stay healthy. Until next week.